Hello everyone. Today I'm going to start a very important topic from classical thermodynamics, that is quasi-static process. Understanding of this topic is really very important as it will help you to understand various boundary displacement work such as constant pressure process, constant volume process, adiabatic process, isothermal process, or any general polytropic process. So all these boundary displacement processes which I have expressed right now undergoes via quasi-static process only or via quasi-static manner only. So this topic will help you to gain a basic thought, or it will help you to gain a basic spirit as to how a thermodynamic process undergoes. Okay, so let us start the quasi-static process understanding. So here you can see I have drawn a very popular arrangement, that is piston cylinder arrangement, right? As you can see, this is cylinder walls and this is piston, right? And we are assuming this piston to be massless as of now, right? And above this piston, there is some load, as you can see, a distributed load, as you can see here with this green dots, right? Whose total weight is equal to W, right? If you add small weight, it will be equal to the total weight W, right? You can assume this to be as a heap of rice or a heap of grain, right? You know that rice, small grains are there, right? Or you can assume as a heap of sand is there, small, very tiny particles are there, which is kept over the top of the piston, right? And there's an atmospheric pressure force which will be always acting on the piston from the top. And below the piston, inside my cylinder, there is a gas. There's a gas. It can be an ideal gas. It can be a real gas. So let's say there's a gas here. Right? And gas is my system. Right? I'm going to analyze this gas for my thermodynamic analysis. Right? So let us try to put the boundary which will enclose or which will entrap my this system. Right? Right? So these are the boundaries. Which separates this gas from surrounding, right? Okay. Now, at this condition, my system is in thermodynamic equilibrium, right? What do you mean by thermodynamic equilibrium? Thermodynamic equilibrium means there is a equilibrium of temperature within my system, means equality of temperature is there throughout, same temperature is throughout my system, right? There's a mechanical equilibrium is there. It means throughout my system one pressure is established, right? Everywhere same pressure is there, and also there is no chemical reaction happening, right? So such that from all aspect it is in thermodynamic equilibrium, right? Thermal equilibrium, mechanical equilibrium, and chemical equilibrium, if it's established all together, then my system will be in thermodynamic equilibrium, right? So at this condition, if this is my thermodynamic equilibrium condition, let's see what properties I can see from here, right? So let's say the pressure of this gas is, initial pressure of the gas is Pi, right? And the initial volume of this gas is Vi. Right? So initial pressure is there at this point of equilibrium condition, and this initial volume is there at this point of initial condition, right? So properties are fixed. If thermodynamic equilibrium is established, it means properties are fixed. Properties won't fluctuate. Properties won't vary, right? As you can see, this internal pressure, this Pi, initial pressure Pi, initial volume Vi is same throughout, and it won't be vary, right? It won't vary, it won't fluctuate. So if thermodynamic equilibrium is established, it means properties are fixed. So I can also say the state of the system is fixed, the condition of the system is fixed. So this is my initial state 1. This is my initial state 1. Initial state 1, right? So state is basically described by its properties. If properties are fixed, it is not varying, it is not fluctuating with respect to time, it is not varying with respect to space, then the state or the condition of my system is fixed, right? So this state is fixed. Let us draw this state or plot this state on my property diagram, that is P and V diagram, right? Okay. So on the x-axis, I'm taking volume, right? And on the y-axis, I'm taking pressure, right? And the initial state is designated by Pi and Vi. So I can plot it over property diagram, right? So this is my state 1. So let's say this is my state 1. This is my state 1. Right? Which is designated by initial pressure and initial volume. Right? Initial pressure and initial volume. Right? So at this state, this is the property. Right? Now, so if this isn't completely in equilibrium, pressure is not varying completely, it means the piston will also not move up, neither it move come down. The piston will not fluctuate, right? If piston will come down, it will compress the gas, so pressure will increase. If piston goes up, so pressure will drop. So the expansion and compression of the gas will happen if the piston will fluctuate, right? So if I have to maintain this pressure, this initial pressure throughout same and invariant with time, I have to ensure that this piston should not fluctuate. It should not come up or come down, right? So equilibrium of the piston is also very important to ensure over here. And how the piston will be in equilibrium? On piston, some weights, some forces are acting, right? As you can see, there's the weight is there, a distributed weight is there, which is kept over the top of the piston, right? There's an atmospheric pressure force acting on the top of the piston, and also this gas pressure force is also acting from the bottom of the piston, right? So under this three pressure forces, this piston has to be in equilibrium, right? So let us apply this equilibrium condition on the piston, right? So the net vertical force on piston has to be 0, right? Then only my piston will not be in unequilibrium condition, right? Right. So what are the forces acting? So weight will act downward, right? Atmospheric pressure will act in the downward direction, and this internal pressure force will be acting in the upward direction, right? So this is pressure of the gas, initial pressure of the gas, multiplied with the cross section of the piston will give me the pressure force exerted by this gas on the bottom of the piston. This will be equal to the weight which is acting downward plus atmospheric pressure force acting downward, right? So this is the condition in which my system will be in mechanical equilibrium condition, right? Okay. Now what we'll do, we will remove very small amount of weight from here. Let's say I'm assuming this is a heap of rice, heap of grains. I'm removing one grain from this total grain, right? From this total grain, I'm just removing one grain. And you know that one grain weight is very, very less compared to this total weight W, right? It will be some in milligrams, right? So if I remove one small weight, right? If I remove only one small weight, let's say this grain I'm removing, one small grain I'm removing from here, right? And because this grain has very, very negligible weight compared to this total weight, so I am assuming this weight to be dW, right? Where dW is tending to 0, right? Not equal to 0, tending to 0, right? Because some weight will be there of that one grain, but it is so less that it will almost equal to 0, right? In kilograms. Fine. Now what will happen when you remove this one grain? There will be some imbalance of forces on the top and the bottom of the piston, right? Because initially this weight plus atmospheric pressure force was balancing gas pressure force from the bottom. But this now weight is reduced. This total weight W is reduced. Slightly it is reduced. Why so? Because you have removed very small amount of weight. So definitely some imbalance of forces will be there, right? Some imbalance of forces will be there, right? So from the top, some weight is reduced now. So now there's a scope for the gas to expand slightly. Gas will expand, right? See, the next step, after you remove this small weight dW, which is very, very less weight, let's see what will the further diagram from here onwards. So as the some amount of weight is out of from the top of the piston, so piston will rise slightly. Very small displacement of the piston will be there in the upward direction due to the removable of this small weight dw, right? So now the piston will be moving slightly upward, right? Let's say the piston position came here, right? So how much distance it has moved up? This much distance, right? So this is dx distance, and you know that from your basic calculus, this dx is tending to 0. Differential displacement is there, right? Dx is tending to 0. Why dx is tending to 0? Because very small imbalance we have created on the top of the piston by removing very small weight. So small displacement will be there, right? But again this piston will come to halt. Why? Because again this rest of the weight will balance the pressure force from the gas, right? Now, so when the piston will move up, the pressure will decrease, right? Because this is a slight expansion process, right? So molecule will move far apart, right? So expansion will be there. So pressure will drop. So let's say the pressure comes from initial pressure to P1 pressure. Pressure has been changed. What is the value of this P1 pressure? It is equal to initial pressure minus some decrement in the pressure, right? Because very infinitesimally everything is happening, right? So very small weight we are removing from the top, right? Which will increase the distance, increase the displacement of the piston. Slight displacement of the piston will be there. Slight drop in pressure will be there. That is dp tending to 0, right? So from this initial pressure, this much pressure will be lost, and again the some pressure will be established, right? So remember here dp is tending to 0. Right? Similarly, what about the volume? Volume will increase, right? Expansion is there, volume will increase. So initial volume will become V1 volume. So V1 is equal to initial volume plus small increment in the volume, right? dV is the small change in the volume by increasing the expansion, right? Due to the expansion, small increment in the volume will be there, right? So here also dV is also tending to 0. Right? So small changes are there, as you can see, right? Now what will happen? Again, leftover grains are already there. So many grains are there. N number of grains are there, right? Now, what will be the weight of the grain now? The weight of the grain will be slightly reduced. If we talk about with the accuracy level, weight of the grain will reduce because this dw amount of grain, small amount of grain I have removed. So this total weight will reduce from w, right? So this will become w dash. The weight is changed. How much weight? It will be initial weight minus dw, right? Right? If you subtract dw's, this small amount of weight which you have removed from the initial weight, you will get a new weight of this total grains here, right? And yes, atmospheric pressure is always acting here. Now what will happen? The system will come into equilibrium. As you can see, system has again come into a thermodynamic equilibrium. Again, the properties are established uniformly everywhere, right? Again, the properties are not varying with respect to time, because again, this much weight which is at the top and this pressure force due to atmospheric will be balanced by this gas pressure which is below the piston, right? So again, there will be a equilibrium condition. So mechanical equilibrium condition will be in such a way that P1 into area of the piston, that will be equal to W dash now, right? W dash plus atmospheric pressure force. Right? Now this will be the equation, new equilibrium condition, right? Because the mechanical equilibrium established, this will be the new mechanical equilibrium condition, right? So the new weight and this atmospheric pressure force acting on the top of the piston will exactly balance this gas pressure force at this state, right? So now we can see there is a equality of pressure everywhere and equality of properties everywhere in the system, right? So because thermodynamic equilibrium is established now, so properties are fixed and now the state will be also fixed, and the state is described by this P1 and V1, right? So I can register now this P1 and V1 and can plot on my property diagram, right? So this is the another state, right? That is P1 V1, right? New equilibrium state is P1 V1, right? Now again we will do the same process now. Same process. Again we will remove one grain again, right? Again we will remove one grain again. Let's say this grain I am removing, right? Remove from the top, right? dW, and we know this is very small weight, right? Tending to 0, right? Now what will happen? Again this removal of this small weight will create imbalance of forces on the top and the bottom of the piston, right? So again you see this W dash will decrease. W dash will decrease because we have removed one small weight from the top of the piston. So W dash will decrease. So on the top of the piston weight is decreased. So again there is a scope of expansion will be there. So gas will expand again very slightly. Why slightly? Because very negligible imbalance we have created by removing very small weight. So next step I am writing here. So again there will be expansion. Again there will be a expansion. Okay. This was the initial, right? Piston was here. Now piston will be moving slightly upward. This is dx distance, displacement is there, right? Piston will move again very slightly. Slight displacement will be there, right? Differential displacement will be there. Dx is tending to 0, right? Now again what will happen? This pressure will fall. Expansion is there, pressure will fall, and this volume will rise up, right? But again by very small amount. So again new pressure will be established, P2, that will be equal to P1 minus dP, right? So from this P1 pressure, some amount of pressure will be dropped and again new pressure will come. Similarly, new volume will come because expansion is there, right? So from this V1 volume, some volume will be decreased and another fresh volume will be established. So V1, so this volume will increase at, right? So V1 plus dV, right? V1 plus dV, right? So new properties are established. New properties are established, right? And again, leftover grains are already there. There are lot of grains, lot of leftover grains are there, right? Okay. Now, again, the equilibrium will be established, right? So under this equilibrium condition, again the mechanical equilibrium will be also established. So let me write the mechanical equilibrium condition over here. Right? So this will be P2 into area of piston, that is equal to now this will be W double dash. This will be W double dash, right? W double dash, right? So this will be W double dash, new weight is there, and this is equal to the W dash minus dW. W dash minus dW, right? Okay. So this will be W dash, which is equal to W double dash is equal to W dash minus dW, right? So slight reduction of weight will be there from this weight to this weight because we have removed one more grain, right? Now under this new weight W double dash and this atmospheric pressure force, the piston will be again in equilibrium, right? Piston will be again in equilibrium. So that is what is writing here, W double dash plus P naught AP. Right? So this is the third step which I have shown to you, right? Because now thermodynamic equilibrium is established, right? Pressure is completely maintained, right? Volume is maintained everywhere. It is not fluctuating. All the properties are now established, right? When the properties are established, I can say the state of the system is fixed, right? So I can plot this state over here. So this is P2 V2, right? So like this we will keep on removing one grain continuously, and you can feel that it will take lot of time, ample amount of time, right? It is very tedious task, right? And but after removing slowly one grain, you will see that small displacement will be there for the piston. Piston will continue to rise up and slowly equilibrium will be established. At every state equilibrium will be established. You remove the grain, again it will rise up, equilibrium will be established. You remove the grain, again piston will rise, equilibrium will establish. Like this, you will see, you will get infinite number of equilibrium states. Right? If you remove all the grains, finally you will have lot of intermediate equilibrium states. Let's say P3, V3, P4, V4, right? Let's say this is P5, V5, right? And finally you are here, right? P6 and V6, right? You are getting infinite number of equilibrium state. More closer will be this equilibrium states, means lesser will be the more the, or can say the more the closer will be this equilibrium states, or in other words, less will be this displacement, you will get more number of equilibrium states, right? You will get more number of equilibrium states. Now you connect all these equilibrium states with a smooth line, right? Connect all these equilibrium states, you will get a smooth line. This is actually the path of the process. Right? Path of the process, right? Which system has undergone from initial state. So let's say this is the final state, from initial state to the final state. This is P5, V5, and this is final pressure and final volume, right? When you remove all the grains, the final volume and final pressure will be established here, right? And this path of the process is very important for us to know, right? So that we can calculate work transfer or heat transfer, because they are path function, right? So to calculate this path, eventually we have to take the process under quasi-static manner only. So this path which you have got, it is via quasi-static manner. Quasi-static process, right? Now if you see any equilibrium state, let's say this equilibrium state is deviated from its previous equilibrium state very negligibly, right? The deviation of equilibrium states, as you can see, it's very negligible. You can see here P1 minus P2 is dP. Very small changes are there in the properties, right? After that, again the equilibrium is established, right? So like this, we keep on doing this type of thing so that we can get the intermediate states, intermediate points, so we can get the path of the process. So this is the quasi-static process. I hope you have understood this important concept, right? This will help you to understand various PDV work also. Okay, thank you.